Let's look at collecting data in a reasonable way. So data and conclusions are based on data everywhere: newspapers, magazines, online reports, professional publications. So you see information all the time. Should you eat garlic to prevent a cold? Will doing Tai Chi 1 hour per week increase the effectiveness of your flu shot? Will eating cheese before going to bed help you sleep better? The problem is all this data, what should you believe when you read or hear this? The big part is, how is the data collected? And that's what we're going to get into. Is a lot of these questions are answered when data is gathered from observations or from an experiment. When we get information that we want to study, the entire collection of individuals or objects that you're interested, you want to learn something about them, is called the population. Where within the population, part of the population that is selected for the study is called a sample. So let's say, for example, that people that watch CSI, these criminal shows, that they expect more. They have these higher expectations based on what they see on TV of the real world, right? So you watch an hour show, and within an hour they've already found the body, they've already gotten an autopsy, they've already, figured out who's guilty. Well, certainly that's not realistic. And so what we could do is we could look and see, do we think people who watch these shows on a regular basis, do they have higher expectation with those that don't watch them? Well, what we could do is we would need to select a sample of people who watch these shows and a sample of people who do not. We'd interview the people and see what their expectations are. And so what we're doing here is what's called an observational study, which is just simply a study that the person conducting the study observes a particular characteristic, such as, do they have higher expectations? And this sample is selected from one or more existing populations. The goal, which is important, of this observational study is to use data from the sample to learn about the corresponding population. Well, suppose a chemistry teacher wants to see the effects on students' test scores if the lab time were increased from 3 hours to 6 hours. Do you think this is an observational study? Well, in this case it's not, because we're looking at what could happen when we increase the lab hours. What's the effect of increasing the lab hours? And this can't be answered by just gathering data, okay, from an observational study. So what we do is what's called an experiment, which is a study in which the person conducting the study looks at how a response variable, okay, so we're going to talk more about variables, but how a response variable behaves under different experimental conditions. So a very big difference between an experiment and an observational study is, within an experiment, the person carrying out that study determines who will be in what experimental groups and what the experimental conditions will be. So the person carrying out the experiment actually gets to say, well, let's increase lab time. What will the lab time be? And the teacher gets to determine that, and which students are we going to put in the 3-hour lab and which are we going to put in the 6-hour lab. Where the observational study, the person that carries out the study does not determine who will be in what groups. So our CSI effect, the researcher did not determine whether or not the people watched the investigative TV show. It just simply asked, it observed based off of all these people it asked, do you believe that, if you watch CSI, that these things really happen this quickly? So observational studies, the purpose is to collect data that will allow you to learn about a single population, or how 2 or more populations will differ. People that watch CSI, people that don't. And it allows you to answer questions Like, what's the proportion of people that think this? On average, how many people think this? Is there an association between people that watch CSI versus people that don't? Ideally, we would like to carry this out with a census, which a census obtains information about the entire population. That means everybody. So whoever you're interested in finding something about, we get the entire population. So why might we prefer to select a sample rather than get the entire population? And this is important because if you want to know about everybody in San Antonio, Texas, well, you may not can get a hold of everybody in San Antonio, Texas. Or if you're testing something like you're measuring how long a battery lasts, well, you got to see how long the battery lasts, right? So after the battery has died, then we no longer can test it. And so the problem is, you know, if we're doing a safety rating of cars and we're crashing cars to see how the airbags are, well, how many cars do you want to crash before finally you say, okay, that's enough? Also, it could be difficult to find the entire population. Like, for example, say you want to know the average length of a fish in a particular lake. Well, you could pick a sample that's representative of the fish in the lake, but certainly you don't want to have to get every single fish in that lake because, one, it could be very difficult to do. And the big key is limited resources. So you want to know how many people in San Antonio drink beer. Well, how are you going to go ask every single person in San Antonio? This takes a lot of time, and you might say, well, I could hire a bunch of people. Well, then that's going to take a lot of money. So when you answer questions like, what is the proportion? What is the average? You're looking at a population characteristic. This is the characteristic, a number that describes the entire population. Where when you look at a sample, you're looking at a statistic, but it's very important that your sample is representative of the entire population. And so we've got to figure out, how can we do that? How can we make sure everybody has been represented in my sample? Well, one way to do this is to take a simple random sample. A simple random sample has a sample size little n, so the number or the letter little n is our sample size, and it assures that everybody in the population has the same chance of being selected. I think of this like putting names in a hat. If I put everybody in this class, your name in a hat, and then I draw names, everybody has the same chance of being selected. Once again, where n, the little n, is used to denote the sample size. So suppose you want to select 10 employees from all employees, so all employees is my population, then my value of n, my sample size, would be 10. To select a simple random sample, what we do is we create a list, and we call this a sampling frame. So I would create a list of all the employees in the firm. I could do something like number each employee with a unique number. You know, I could start with 1 through however many employees. And then I can use what's called a random digit table or a random number generator to generate and find these 10 random people. I have to be sure that everybody must have an equal chance. That means if you're full-time, if you're part-time. Okay, and so everybody has a chance of being selected. How you use a table like this, and you can find these tables online everywhere, is you might say, well, our company has 250 employees. Because 250 is a 3-digit number, I'm going to start here. I just picked a row. I randomly selected row 6, and I'm going to select 3-digit numbers from the table. If the number's not between 1 and 250, then I just ignore it. So the first one I see is number 93. 876 is not between 1 and 250, so I ignore it. 799 gets ignored, 562, 565, 842, 644. Next good number is 101, 22, 47. I ignore the 511. I ignore 947. And I continue to do this until I get my 10 random samples. And this table was created by a random number generator that would give me a sample to be able to pick these employees. I go back to my list now. I find employee number 93 and I pick them. I go down the list, I find employee 101 and I pick them, and so on. All right, let's look at what's called sampling with replacement. Basically, this is you draw a name from a hat and then you put their name back in. So somebody could win twice. So this allows an object or an individual to be selected more than once for a sample. We pick Bob, we put Bob back in, and then we could pick him again. This is something that's rarely used. Okay, it might be, again, a contest where somebody could win more than once. Typically what you see is sampling without replacement, which says once an individual or object is selected, they're not going to be replaced and they cannot be selected again. And this is a lot more common, because certainly if you're sampling something and you're asking somebody a question, you don't want to ask that same person the same question again. Although sampling with and without replacement are different, they can be treated as the same when the sample size, remember that's little n, is relatively small compared to the population. In other words, no more than 10% of the population. So what about this sample size? I mean, in a perfect world, you would think you want to sample as many people as you can. So I have a sample here of SAT scores, and I can see even as my sample is getting smaller and smaller, as long as I'm taking a representative sample, I'm still not getting many way below, many way above these values, which shows even at 50, I'm getting a very representative sample. So it is possible to obtain a simple random sample that is not representative of the population, but this is only likely when you have a very, very small sample. All right, besides the simple random sample, there certainly are other ways to sample data. Stratified random sample is where you first divide the population into non-overlapping subgroups. Something that would be non-overlapping could be students' homeroom. You're only in one homeroom. Or it could be male versus female. You're either a male or you're a female. You can't be both. And these subgroups we call strata. We then separate each one of these, and within each strata, we do a simple random sample. And so the strata are subgroups that are similar, homogeneous, based upon some characteristic of the group members. Again, it could be all math majors, all computer science majors, and so on. So they have something in common, a common characteristic. Stratified random sampling is often easier to implement and is more cost effective than simple random sampling, because you can go grab groups, and within that group you could look at your simple random sample. So let's suppose we want to estimate the average cost of malpractice insurance for doctors in a particular city. We certainly could find all the doctors in this city and we could go get a simple random sample. Or what we could do is we could put them in these strata, in these groups, and then do a simple random sample of just surgeons, just internists, and family practitioners, and so on. And so we could just look at a particular strata and do our simple random sample within that. Certainly the real advantage of this is it allows you to make more accurate inferences, okay, than just randomly going out and grabbing people. And it is much easier to produce accurate estimates, okay, because once again we're looking at homogeneous groups, so all surgeons, and then within that group. Cluster sampling is a lot like the stratified. We select people, we put them in groups, we make sure that they're non-overlapping, we call these clusters. The big difference is we take an entire cluster. Where the stratified, we went within the strata and then we did a simple random sample. Here we put people into clusters and then we take the entire cluster. So for example, let's say a large urban high school has 600 senior students, all of whom are enrolled in a first period homeroom. So everybody has a different homeroom class. There are 24 senior homerooms, each with approximately 25 students. The school administrators want to select a sample of 75 seniors to participate. Well, you could go out and you could just pick 75 seniors, or what you could do is you could randomly select 3 senior homerooms and then take all of those, that's your cluster, the homeroom, and take all of those from those homerooms. So certainly this is more ideal when the cluster mirrors the characteristics of the population. In other words, within this cluster, certainly they're all in the same homeroom, but there's going to be a bunch of different type students in there. So don't confuse this. Stratification, I set up my different strata, and then I randomly select individuals from each group. Where the clusters, I put them into clusters, and then I select an entire cluster. So that's the big difference here. Something else we could do is this 1NK systematic sampling, where we select an order arrangement of a population by first picking a starting point at random. So I start with the third person, and then I count every kth individual. So maybe I start with person number 3, and then I pick every third person. And K is often selected so that a certain sample size is produced. Like you're interested in a particular sample size, and I can do that. The capital N gives you your population size. The little n gives you your sample size. And I can find this by taking my population and dividing by my sample. So let's say you want to select a sample of faculty members. You could get a list, a phone directory of all the faculty members. You could start with a particular faculty member, say the 20th one in the list, and then you could select every 20th faculty member after that. This certainly works well if you have a really, really long list. You know, if you're picking the 20th faculty member and there's only 25 members, this probably isn't a very good technique. Another sampling technique is called convenient sampling. It's exactly what it sounds like. It's convenient. It's easy to get these individuals. So let's say I asked you to gather a sample of 20 students. Well, why not just get them in one class? That's easy, right? The problem with that is this would not be represented of the college, of all the students at your college. Because if you're picking everybody in your next class, well, maybe your next class is math majors. And so I'm not representing the entire college population. So typically this is something you don't want to use, and you actually see it used a lot with voluntary response. So in other words, people volunteer because they're motivated for some reason, they have a strong opinion, and certainly these aren't going to be the type of people that are going to be representative of the population. All right, let's see if we can figure out the sampling method. So the Educational Testing Service needs a sample of colleges. They first divide all the colleges into 6 subgroups. Okay, so I have these 6 groups: small public, small private, medium private, large public, and large private. Then they randomly select 3 colleges from each group. This would be your stratified. I put them in groups of these small groups, that's my strata, and then I randomly select within those groups. How about a county commissioner wants to survey people in her district to determine their opinions on a particular law that's up for adoption. She decides to randomly select blocks in her district and then will survey all in those blocks. Notice my emphasis on the word all. I've put them in these clusters and I took the entire cluster. A local restaurant manager wants to survey customers about the service they receive. So each night the manager randomly chooses a number between 1 and 10, and then he gives a survey to that customer, and then every 10th customer after that. So this is my kth systematic sampling. All right, this is a very famous example of a blunder that happened. In 1936, FDR had been president for 1 term. The Literary Digest predicted that Landon would beat FDR by 57 to 43%. How they did this prediction is they mailed over 10 million questionnaires to names that were drawn from lists of automobile owners and telephone owners. And over 2.3 million people responded, a huge sample. At the same time, this dude, George Gallup, came along, and he only sampled 50,000 people, but he predicted that Roosevelt would win. And Gallup's prediction was ridiculed as naive. But actually what happened is the Digest had predicted the winner in every election since 1960, so they were more well-known. And they based their predictions on the largest response, the biggest sample size. But guess what? Roosevelt won. They were wrong. And so the size of the Digest error was staggering because of a bias. Think about it. 1936, who owned cars and telephones? Probably only rich people. And so only the rich people were the people that were voting for Landon. So this is a classic example of what's called bias, which is the tendency for samples to differ from the corresponding population in some systematic way. And we have different sources of bias. We have a selection bias, which suppose you take a sample by randomly selecting names from the phone book. Some groups will not have the opportunity of being selected. Think about people with unlisted numbers. Think about people without phone numbers. Think about people that only have cell phones. So you've underrepresented high-income families, low-income families, and young adults. The selection bias occurs when the way the sample is selected systematically excludes some part of the population of interest. This also might occur if you only have volunteers, okay, or people that are self-selected and used in a study. Another source of a bias is a measurement or response bias, and this occurs when the method of observation tends to produce values that systematically differ from the true value in some way. Think about if you have something improperly calibrated, okay, and use a scale to weigh items. Certainly, different people are going to get different weights. Also, people tend to not be completely honest if they're asked about something like illegal behavior. Have a police officer come around campus and ask how many students smoke pot. What do you think they're going to tell the police officer, right? Even the appearance or behavior could sway the way somebody answers. What do you think? Do you trust men with mustaches? Well, what if the guy asking you this question has a mustache? Also, the way questions can be worded can influence the response. So look at this example. It says it's estimated that disposable diapers account for less than 2% of the trash in today's landfills. In contrast, beverage containers, third-class mail, and yard waste are estimated to account for about 21%. Given this, in your opinion, would it be fair to tax or ban disposable diapers? Well, they've already led you. They've worded this in a way that's going to influence my answer because it's only 2%. What's 2%? This looks to be the other problem. And so a lot of times they can word it in a way to convince you how to answer. Also, a huge source of bias is people that don't respond. So responses are not obtained from all the individuals that were actually selected. The phone rings, it's dinner time. You ain't got time to answer any questions, you hang up. So normally what happens to minimize this is you do a follow-up call. And so it might be a follow-up call, it might be another follow-up letter, and so on. Well, will increasing the sample size reduce the effects of bias? Well, we just saw on FDR, no. You can have 1 million people in your sample, and a sample of 100 could be better if, when I selected these people, my selection wasn't flawed, and I had a high response time. So if your non-response is high and your method of selection is flawed, who cares how many people you have? Okay, let's look and see if we can figure out the bias here. Suppose you want to estimate the total amount of money spent by students on textbooks each semester at a local college. Certainly you could collect register receipts for the students as they leave the bookstore during lunch one day. What's the problem here? Well, I mean, certainly this is very easy and convenient that we said don't do. It's a very easy way to collect data, but the problem is, what about the people that buy their books online? What about people that rent textbooks? So they're not even going to be in this sample. What if we want to find the average value of a home in Plano? And so what we do is we find averages of price of homes that are listed for sale with a realtor. What's wrong with this? Well, I want to know the average value of home. All this is going to give me is people that are listed with that realtor that's selling their home. And that's the problem with this is if I want to know overall the average value, well, this is giving me nothing. This is giving me the average value of this realtor that people are selling their home. All right, let's look at this article, What People Buy from Fast Food Restaurants. It says this was reported that the average number of calories consumed at lunch for this city fast food restaurants was 827. The researchers selected 267 fast food locations at random. The paper states that at each of these locations, adult customers were approached as they entered the restaurant and asked to provide their food receipt when exiting to complete a brief survey. Will this study result in data that is representative of the population? Well, let's look at all the pieces here. What is the population of interest? It's people who eat fast food at these restaurants. Was the sample selected in a reasonable way? Yeah, it said they randomly selected some adults. Is it likely that this sample is representative of the population of interest? Well, yeah, because if we selected a bunch of different fast food restaurants, so that seems reasonable. Are there any obvious source of biases? Well, certainly you could have people that refuse to participate. Also, you could have this response bias since customers were approached before they ordered. But I mean, you could think of a lot of different things like the time of day could have been a bias. Maybe more people buy fast food for lunch than they do for dinner. Let's look more into experimental design and experiments. So suppose we're interested in determining the effect of room temperature on the performance of a first semester calculus exam. You know, you guys use every excuse in the book. I failed my exam because it was too cold. So what are we looking at here? What variable are we measuring? Well, we're looking at their performance, the student's performance. This is what's called the response variable. The response variable is a variable that is not controlled by the experimenter, and it's measured as part of the experiment. That's what we're interested in measuring. What variable will explain the results on the calculus exam? Well, that could be the room temperature, which is called the explanatory variable. These are variables that have values that are controlled. We can control the room temperature, and these also are typically called factors. So we decide, let's do an experiment and let's use two temperature settings, 65 degrees and 75 degrees. Well, what we call a treatment is our experimental conditions. So our treatments in this case, we'd have two, which would be the temperature at 65 degrees and the temperature at 75 degrees. So suppose we have 10 sections of first semester calculus that have agreed to participate in our study. So on who or what will we impose the treatments? Well, it'd be these 10 sections, right? These are what we call our subjects, or our experimental units. So in other words, they're the smallest unit to which the treatment is applied. Should the instructors of these sections be allowed to select to which room temperature their section is assigned? Like, I want my room temperature at the better temperature. Well, no, we're not going to allow them to do that because, of course, they probably would select the better temperature for their students. This is what's called a confounding variable, where the effects, we really can't distinguish them because it would be difficult to tell, was it the temperature or was it something else? And so our goal here is to determine the effects of the treatment, 65 degrees, 75 degrees, on our response variable, how the student did on their test. To do this, you must consider there's other potential sources of variability in the response. So you either eliminate them or you ensure they produce a chance-like variability. So think about what could be some other variables that could affect this response. What about time of day? What about the instructor? Maybe the textbook. Maybe every class didn't use the same textbook, or even the ability level of the students. Heck, who knows? Maybe one class was a very high-level class. So in an experiment, these other variables would need to be controlled, and this is what's called direct control, where we hold these other variables constant. In other words, we only select one time of day. We only select one instructor for these 10 different sections. Make sure they all use the same textbook. Make sure their ability level is pretty much on average all the same. Well, the problem is can the experimenter control these other variables? Well, we could if we made sure that the time of the day, the instructor was the same and everything. But what about the variables that the experiment can't directly control? So what can we do with these confounding variables? The experimenter can't necessarily control who the instructors are. If you're given 10 different sections, it's highly unlikely nobody at UTSA teaches 10 different sections. So you're probably not going to get the same instructor. So another way you could control a variable is to block that variable. In other words, we use each instructor as his or own block. Then sections of each instructor would be randomly assigned to the two treatments. So we're looking at, well, what about other variables that we cannot control directly? Or a lot of times they're variables we don't even think about. This random assignment should evenly spread out all other variables that we are not controlling directly into different treatment groups. We definitely expect these variables to affect all the experimental groups in the same way. Therefore, their effects are not confounding. So what we might do is we randomly assign the 10 sections of the first semester calculus to the 2 treatment groups. So let's choose numbers between 1 and 10, put them in a hat. I randomly select 5 numbers and they go into treatment 1. And then the other 5 go into treatment 2. So I did not pick out of these 10 sections. I just randomly selected which treatment group they would go in. There's 10 sections, so this is called replication. In other words, replication ensures that there is an adequate number of observations for each experimental condition. Okay, let's look at some key concepts of this experimental design. We talked about direct control, where this holds potential confounding variables constant, so their effects are not confounded with the treatments. Blocking uses potentially confounding variables to create groups or blocks that are similar, and all experimental conditions are then tried within each block. Random assignment removes the potential for confounding variables by creating equivalent experimental groups. This random assignment is very critical, a very critical component of a good experiment. And then we look at replication to ensure that there is an adequate number of observations for each treatment. So what to do with these potentially confounding variables? Well, if they're known, and that's the hard part, is sometimes they're not even known. If they're known, then we use this direct control and blocking. However, a lot of times they're not even known that some other variable is causing a problem. And so this is where the random assignment comes in. So a completely randomized design is an experiment in which the experimental units are randomly assigned to treatments, and this is called a completely randomized experiment. So you have experimental units, you have a random assignment, randomly put some in treatment A, randomly put some in treatment B. I measure a response for treatment A, I measure a response for treatment B, and then I compare the 2 treatments. If I have a randomized block design, then this incorporates blocking by dividing the experimental units into these homogeneous blocks, and then randomly assign individuals within each block to these treatments. So I have my experimental units and I create my blocks first, and then I do my random assignment. And then I do my measurements for each one. And then I can compare everybody in block 1, everybody in block 2, and then finally I can compare the 2 blocks. Let's look at an example of an experimental design. Can moving their hands help children learn math? So an experiment was conducted to compare 2 different methods for teaching children how to solve math problems of this form. So one method involved having students point to the 3 plus 2 on the left side of the equal sign with one hand, and then point to the blank on the right side of the equal sign before they filled in the blank to complete the equation. The other method did not involve using hand gestures. So what we wanted to do is compare these 2 methods. We got 128 children, ages 9 and 10. They were randomly assigned to the 2 experimental conditions. This is an example of what type of experimental design. Well, this is completely randomized. The 128 children are just randomly assigned into the 2 treatment groups. So I have 128 children. I randomly assign one group that used the hand gestures, the other group that didn't. I get my measurement, and then I compare the two groups. Well, suppose you're worried that the gender might be related to performance on a math test. So what you could do is you could use direct control of the gender and use only boys or only girls, but then your conclusion can only be generalized on that group. Another thing you could do is blocking, where you could create two blocks, one of girls, one of boys. Then you randomly assign the girls, you randomly assign the boys, and then you compare the two treatments. So this would be an example of randomized block design. So we have 128 students and we block them by gender. So 128, I first create my blocks of girls and then boys, and then I do my random assignment. Hand gestures, no hand gestures. I get my measurement. I compare the girls, hand, no hand. Compare the boys, hand, no hand. And then finally, I make a final comparison on the boys and the girls. So let's go back of this whole deal of our calculus students, that we put them in these two treatment groups of 65 degrees and 75 degrees. We do not have a control group, which a control group is an experimental group that didn't receive any treatment. In other words, it would allow the experimenter to assess how the response variable behaves when no treatment is being used, but it also provides a baseline against which the treatment groups can be compared to determine whether the treatment actually had an effect. And you see this a lot in experiments with humans, that they use what's called a placebo. In other words, the placebo looks exactly like the pill everybody else took, but it has nothing in it. There's no active ingredients in it. So consider Anna, a waitress. She decides to perform an experiment to determine if writing "thank you" on the receipt increases her tip percentage. She plans on having two groups. On one group, she will write "thank you" on the receipt, and on the other group, she doesn't write anything. So which of these would be the control group? Well, once again, as if we go back here, we see that a control group allows the experimenter to assess how the response variable behaves when the treatment is not used. So our control group would be the people that she did not write the "thank you" on the receipt. Would the students in each section of calculus know to which treatment group they were assigned? Well, if they knew about the experiment, they probably know the difference between 65 degrees and 75 degrees. But an experiment in which the subjects do not know which treatment they were in is called a single blind experiment. So this experiment is probably not blinded if the students knew about it. A double blind is where the subject and the person actually doing the experiment, who's measuring the response, they don't know either. So that's a double blind. So when you use volunteers, bless me again, as subjects in an experiment, remember using volunteers is never a good idea. Okay, however, it is actually a common practice. Suppose you want to use anybody between the ages of 25 and 30 that smokes, and you have volunteers. So then what you want to do within that is get a random assignment of the volunteer to treatments, and then this will allow your cause and effect conclusions. But it does limit the ability to generalize to the entire population. So the only way to show a cause-effect relationship is with a well-designed, well-controlled experiment. Let's look at an example, killing newborns. Researchers for the National Institute of Child Health and Human Development studied 208 infants whose brains were temporarily deprived of oxygen as a result of complications at birth. These babies were subject in an experiment to determine if reducing body temperature for 3 days after birth actually improved their chances of surviving without brain damage. So the experiment was summarized in a paper that stated infants were randomly assigned to usual care, that's my control group, or whole body cooling. So the researchers recorded whether the infant survived, yes or no, and if the infant had brain damage, yes or no. So let's look at this experiment. So what is the question the experiment is trying to answer? Well, they're trying to answer, does chilling newborns whose brains were temporarily deprived of oxygen at birth, will that actually improve the chance of surviving without brain damage? The experimental treatments in this case were usual care and whole body cooling. The response was our two response variables, survival and then brain damage. The experimental units were the 208 babies, and the description of the experiment, though, doesn't say how they were selected, but it's unlikely it was random. So does the design incorporate random assignment of experimental units to the different experimental conditions? Well, they were randomly assigned to one of the experimental conditions. And in this experiment, the usual care group served as our control group. The experiment did not involve blinding. Okay, it may have been possible to blind the person who makes the assessment of whether or not there was brain damage, but probably was not necessary in this experiment. This is an example of a well-designed experiment. Researchers were able to use the results to be able to conclude that cooling did reduce the risk of death and disability of infants deprived of oxygen at birth. Another example says spanking lowers a child's IQ. Spanking can lower IQ. Smacking hits kids' IQ. So in this study, these investigators followed 806 kids ages 2 to 4 and 704 kids ages 5 to 9 for 4 years. Their IQ was measured at the beginning of the study and then again 4 years later. So the researchers found that at the end of the study, the average IQ of the younger kids who were not spanked was 5 points higher than that of the kids who were spanked. For the older group, the average IQ of kids who were not spanked was 2.8 points higher. All of these headlines imply that spanking was the cause of the difference in IQ. Is this reasonable? I mean, the problem is you're drawing a conclusion based off of, you're generalizing from the sample to the population. This is only reasonable when a random selection is used to obtain the sample. A change in response is caused by experimental condition or cause and effect conclusion when there is a random assignment of experimental units to experimental conditions. So in other words, this implies for observational studies, it's actually not possible to reach this cause and effect conclusion. It is possible to generalize from this sample. With experiments, that's where you can reach the cause and effect conclusion. So if an experiment incorporates both random assignment to experimental condition and random selection of the experimental units from some population, then it is possible to reach some cause and effect. So if we revisit this, these conclusions are not reasonable because this study had no random assignment of experimental units to experimental condition.